Hey everybody, Rob here from Get Some Systems. We're going to go over the analog interface. And so how this fits into the project is you've got two sensors, a thermocouple sensing the temperature inside the toaster, and a little chip from Microchip sensing the room temperature. And so what we do is we connect those outputs into an analog circuit to accomplish some things so that we can get a good reliable signal to sample with our ADC. And so that's what this is about. So start with the thermocouple, and so thermocouples work by heating up one end of one end of the thermocouple, which is two metals welded together, and it creates a potential difference on the other end, and that's how you get your voltage. And so if you go read about these for type K, you find out they're about 40 microvolts per volt, or 40 microvolts per degree C. And so that's really not very useful for us because we can't reliably sample 40 microvolt signal just because it's way too slow, way too low. So we need to boost that up a little bit. So what I did is I developed this simple two-stage op-amp circuit, two-stage amplifier out of op-amps. So the op-amps are MCP 617 from Microchip, and since the thermocouple is a differential signal, it's got two lines and we want to amplify the difference. We want our first stage to be a differential amplifier so we can amplify the difference between the two wires from the thermocouple. So this is the thermocouple right here, and we've got V1 and V2 is a potential difference between the two pieces of metal of the thermocouple, and we run those into the first stage of our amplifier circuit. And so if you're not familiar with these, go Google around a little bit, and when you do, you'll figure out the way they work is voltage output of a differential single stage op amp is going to be, in our case, this resistor over this resistor. So as long as this and this are the same, the 2/8 are the same, and then these two resistors are the same, you can use this equation of these two over these two times the difference in voltage here. So that's what we did. We took our output is going to be 200K over 8K times the difference, and so our difference will be 40 microvolts. So our gain in this op amp works out to be 25. So if you multiply 40 microvolts by 25, you'll get 1 millivolt. So the output here now is going to be 1 millivolt per C. And that's still a little too small. I tried using that and it's just still too small. It's kind of in the noise and you don't get reliable samples out of that. So what you want to do is run that through a second stage. So because of all of the division and whatnot we discussed in the firmware videos, I wanted to make this 8 because it's a lot easier for me to divide 8 by 2 digitally. So I wanted to run this through an amp and get 8 millivolts per degree C out. So I decided to just hook up a little non-inverting amplifier. And so the second stage is this non-inverting amplifier where V out equals V in times 1 plus these two resistors in the feedback path over this resistor. So that works out to 1 plus 6.8K plus 0.2K or 7K. And so if you calculate that out, you'll get the output equals the input times 1 plus 7. And that gives us a gain of 8. So that gives us our 8 millivolts per degree C on the output. And so that is tied directly into the one of the ADC pins on the microcontroller, and that's where we get our thermocouple temperature sample from, is right here, this output. And the other temperature sensor is MCP 9700A from Microchip, and that's down here, and that outputs 10 millivolts per degree C. And this probably doesn't need to go through an amp, but since I had to do all this work up here for the thermocouple, I decided it wouldn't hurt to run this through a unity gain buffer. Basically what this does is it takes that signal and outputs it at the same voltage, but it allows the whatever you connect it to draw a lot more current. So this is why we don't really worry about our ADC time, 4 microseconds should be plenty, because this signal is a lot more powerful now. Even though we're outputting the same voltage, we can push a lot more current through there. So one other note, I guess this same technique with the unity gain buffer was used for my voltage divider for my ADC reference voltage, because I used a pot that had a huge resistance, and my signal wasn't powerful enough to source the signal reference for the ADC10. So I had to run that through this exact same type of circuit. It's unity gain buffer, and it's not drawn up in the schematic because it's so simple, but if you have any problems with your sampling, make sure that your resistors aren't too big for your signal reference for your ADC. And that's it. This is pretty simple too. Two-stage op amp. First stage is a differential input. Second stage is a non-inverting op amp. And this is how we got our 8 millivolts per degree C. And here all we do is buffer our signal just so we don't have to worry about, and really, as I said, you probably don't need this, but while I was working with all these op amps, I figured it wouldn't hurt to put a unity gain buffer on the output of this chip just in case, because I was kind of tired of running into one headache after another. And so that's it for the analog interface.